Nonlinear data structures. There are two types of nonlinear data structures: tree and graph. Trees in data structure. A tree in data structure or computer science is a widely used data structure that emulates hierarchical tree structures with a set of linked nodes. Nature of a tree. In normal nature, we see tree as having leaves, branches, and a root. In computer science views, it is the opposite of it. The tree is upside down and the root node is the parent node, leaves, branches, and nodes. What is a tree in a data structure? A tree is a finite non-empty set of elements. It is an abstract model of hierarchical structure, consists of nodes with a parent-child relation, applications, organization charts, file systems, and programming environments. Here is an example using computers where it is used for sales, manufacturing, research and development, both US and international, laptops, desktops, Europe, Asia, and Canada for international. Tree representation. Tree is represented as shown in the figure. It has root, parent, left child and right child, siblings, leaf, right subtree and left subtree. Root, the topmost node is known as root, the one here labeled one. Children, parents, siblings have same parents. Leaf has no child. Trees in data structures. Tree nodes, each node can have 0 or more children. A node can have at most one parent. Binary tree. Tree with 0 to 2 children per node. Tree, binary tree. Trees terminology: root, no parent. Leaf, no child. Inferior, non-leaf. Interior, which it has no leaf. Height, the distance from root to leaf is known as height. Example tree. Here is an example Semi's, for example, Semi's home page in his laptop or desktop, teaching, research activities, and papers presentations. Tree terminology: path traversal from node to node along with edges results in sequence called path. Root, node at the top of the tree. Parent, any node except root has exactly one edge running upward to another node. The node above it is called parent. Child, any node may have one or more lines running downward to other nodes. Nodes below are children. Leaf, a node that has no children. Subtree, a node can be considered to be the root of a subtree, which consists of its children and its children's and its children and so on. Tree terminology: root, node without parent, which is A in the given figure. Siblings, nodes with the same parents. Internal node, node with at least one child, A, B, C, and F. External node, leaf, node without children, as you can see in the figure: E, I, J, K, G, H, D. Ancestors of a node: parent, grandparent, grandparent, great grandparent, etc. Descendant of a node: child, grandchild, great grandchild, etc. Depth of a node: number of ancestors. Height of a tree: maximum depth of a node. Degrees of a node: the maximum number of its children or its number of children. Degree of the tree: the maximum number of its nodes. Subtree, tree consisting of node and its descendants, is called as subtree, which was given beside. General trees. Trees store data in a hierarchical manner. Trees have layers of nodes where some are higher and others are lower. Root node is A. A's children are B, C, and D. E, F, and D are leaves. Length of path from A to E is 2 edges. Trees have layers of nodes where some are higher and others are lower. Used to represent hierarchical data: B, CS, and C. Section A and Section B as given below the group. Group 1 and Group 2, Group 3. As you can see, here is another representation of hierarchical data from first tree. Continue. A collection of entities is called nodes. Tree is a nonlinear data structure and it's an hierarchical data structure. Tree traversal. Unlike linear data structures, array, linked list, queues, and stacks, etc., which are linear data structures which have only one logical way to traverse them, trees can be traversed in a different ways. Traversal is a process to visit all the nodes of a tree and may print their values too. Because all nodes are connected via edges, links, we always start from the root head node. Continue. That is, we cannot randomly access a node in a tree. There are 3 ways which we can traverse a tree: in order, pre-order, and post-order. In-order traversal. In this traversal method, the left subtree is visited first, when the root and later the right subtree. We should always remember that every node may represent a subtree itself. In order, left, root and right. In order, we start from node A, the parent node, and following in order traversal, we move to its left subtree. B is also traversed in order. The process goes on until all the nodes are visited. The output of in-order traversal of this tree will be D, B, E, A, F, C and G. In-order algorithm. The steps to be followed while traversing in order is recursively traverse left subtree. Step 2, visit the root node. Recursively traverse right subtree. And pre-order traversal. In this traversal method, the root node is visited first, then the left subtree and finally the right subtree. Pre-order, root left and right. Pre-order, we start from A and following pre-order traversal, we first visit A itself and then move to its left subtree. B and B is also traversed pre-order. The process goes on until all the nodes are visited. The output of a pre-order traversal of this tree will be A, B, D, E, C, F and G. Algorithm, until all nodes are traversed, we should follow these steps. We should first visit root node. Next step, we should recursively traverse left subtree. Step 3, recursively traverse right subtree. Post-order traversal. In this traversal method, the root node is visited last, hence the name is post-order traversal. First we traverse the left subtree, then the right subtree and finally the root node. Post-order traversal, left, right and root. In post-order traversal, we start from A and following pre-order traversal, we first visit the left subtree B. B is also traversed post-order. The process goes on until all the nodes are visited. The output of post-order traversal of this tree will be D, E, B, F, G, C, A. Algorithm, we should follow the following steps. Step 1, recursively traverse left subtree. Step 2, recursively traverse right subtree. Step 3, we should visit the node, root node. Operation on tree, insertion, deletion and search. Insertion algorithm, if the root is null, then we must create a root node. If root node exists, then compare the data with the node data while until insertion position is located. If data is greater than node, data will go to the right subtree, or else if it is lesser, if it will go to left subtree. End while insert data. And if search algorithm, if root data is equal to search, data return root, else while data is not found. If data is greater than the node, then the data will go to right subtree, or else it will go to left subtree. If data found, return node. And while the return data, if return data is not found, then it will end task. Deletion algorithm. Types of trees. There are 3 types of trees. The large number of 3 types are there, but however the 3 types are specifically used in majority of the time, both in real world and both in computer science. The types are binary trees, B trees and heaps. First is binary trees. Binary tree follows the rule that each parent node has no more than 2 child nodes. This means that a binary tree can look like this, given in the figure. There are types of binary trees, 3 or 4. There are strict binary tree. A strict binary tree is a binary tree in which a root can exactly have 2 children or no children at all. That means there can be 0 to or 2 children, more than 1 children of any node. Complete binary tree. Complete binary tree is a strict binary tree in which every leaf node is at the same level. That means there are equal number of children in right and left subtree for every node. Extended binary tree. An extended binary tree is a binary tree transformation of any binary tree into a complete binary tree. The transformation consists of replacing every null subtree of the original tree with special nodes. The nodes from the original tree are then called as internal nodes, while the special nodes are called as external nodes. Extended binary tree. A binary tree with special nodes replacing every null subtree. Every regular subtree has 2 children and every special node has no children. Binary search tree example. The value at any node greater than every value in left subtree, smaller than every value in right subtree. For example, in this tree, Y is the parent node and X and Z are the children node. Y is greater than X, but Z is greater than Y. Values in the left subtree less than the parent, values in the right subtree are greater than the parent. Fast searches in binary tree, maximum of log and comparisons. There is an example for that. Binary trees example, we can differentiate between binary search tree and non-binary search tree by referring this example. B trees, there is another type of search tree called as B tree, in which a node can store more than one value or key, and it can have more than two children. B trees can be defined as follows. B tree is a self-balanced search tree with multiple keys, in which every node and more than two children for every node. Operations on B tree, there are three operations: search, deletion and insertion, as seen in the normal tree. Another type and last type of a tree is a heap tree. Heap tree is a special case of balanced binary data which is in a tree form structure, where the root node key is compared with its children and arranged accordingly. If alpha has a child node beta, then alpha, which is a value is or key, is greater than the value of beta. A heap can be of two types: minimum heap and maximum heap. Maximum heap, where the value of the root node is greater than or equal to either of its children. Maximum heap insertion is done in using these numbers in this way. Maximum heap deletion. Maximum heap construction algorithm or insertion algorithm. We should create a new node, assign new value to the node, compare the value of this child node and its parent. If value of the parent is less than the child, then swap them. Repeat step 3 and step 4 until heap property holds. Max heap deletion algorithm: remove root node, move the last element of the last level to the root, compare the value of this child node with its parent. If value of the parent is less than the child, then swap them. Repeat step 3 and 4 until heap property holds. Minimum heap, where the value of the root node is less than or equal to either of its children. Minimum heap insertion 1 and minimum heap deletion. Thank you.